Hello everyone. So today's video is going to be the first physics devoted video on this channel. I've done biology, geology, and that stuff. Some of it, forces and tension and all that, kind of falls into physics, but none of the videos, apart from the experimentation and report reflections and all that kind of stuff, none of that actually falls into the idea of physics itself. And so today's video is going to be a little different, and I'm going to be discussing the three key electrical concepts. These include current, voltage, and resistance. So without any further to do, let's just get straight to the whiteboard and we'll start learning about these concepts. Okay, so let's begin with current. Current is the rate of flow of charge. What does this mean? This means the amount of charge that flows over a specific amount of time. Okay? Now, when I talk about charge, what is it that I'm exactly referring to? Because there are many things that are charged when it comes to science, right? You can have charged protons, you can have electrons, and you can also have ions, because ions are charged as well. So what exactly is it that we are referring to when we talk about the rate of flow of charge? When we're talking about current, what charge are we referring to? Well, it's pretty much all of them, but I can assure you that in most cases, and pretty much all the cases that I guess we'll come across, we're talking about the charge. When we talk about charge in current, we're talking about electrons. Why? Because think about it. When we're talking about current, we're talking about energy flowing through wires. Now, the three options that we have, there's electrons, there's protons, and then there's ions. And if this is my wire, and I need to push any of these through, if I try really hard, I'll be able to push all of them, right? But it's gonna be really easy for me to push the electron. It's going to be extremely hard for me to push the ion, and it's going to be, well, also extremely hard to push the proton, because the electron is the most smallest out of all of them. And just to give you a scale, the electron is 1,800 times smaller than the proton. And so when it comes to pushing things through a wire, you can say that it's the easiest option over here is electrons. Electrons are the easiest to push through a wire. And so there's a term for this, and the term is energetically favorable. It is energetically favorable for the electron to flow through the wire rather than the proton to flow, or the ions to flow through the wire. And that is why when we every time we refer to current, we're always saying electrons flowing. That is current, right? And the rate of flow of charge. So we're talking about electrons, okay? And when we say rate, right, we often have a fraction, and here it's charge over time. So let's look at that as well. The symbol for current is I. Now, we already established that it's charge over time. But another way we can look at this is we can take their symbols. The symbol for charge is Q, and the symbol for time, we all know, is T, so Q over T. Another way we can look at this is the unit for charge is Coulomb. And the unit for time, in this case, is seconds. And so Coulomb over seconds is ampere. So current is charge over time, is Q over T, is Coulomb over seconds, is ampere. And remember, the symbol for coulombs is Q, and the symbol for seconds is time in this case. And so the symbol for current is I, and it's measured in amperes. Remember this, the symbol for current is I, and it's measured in amperes. Now, if we're measuring the amount of charge that flows through a specific amount of time, we're measuring, as we can see here, the number of Coulomb charges that are going through a piece of wire. So, to put this into perspective, we could say that we're measuring the number of electrons that are flowing through a specific point in a specific time. So let's say we measure how many electrons go through this point in 1 second, and we find that 1 coulomb of charge is going through at 1 second equals 1 amp. So our current is 1 amperes. And so when we're measuring current, we only need 1 point, as we can see here, right? And so that is why most of us will notice is that when we have an ammeter, it's placed in series because we only need the measurements for 1 point. Okay? And then there's this one extra thing, and then there's this one last thing when we look at the introduction for currents. It's electron flow versus current flow. So let's quickly take a look at that. Back then, when science wasn't as advanced, people didn't know which direction current flowed. Let alone that, people didn't know if current had a direction. So back then, Benjamin Franklin in 1750, around 1750, gave directions or gave the type of electricity. He said there was positive energy and there was negative energy. And intuitively, he said that energy flows from positive to negative. And so when we did later research, we found that there is a positive and negative side, but it's not. Energy doesn't flow from the positive side to the negative side. Rather, it flows from the negative side to the positive side. And why? This is because electrons in the negative side are much easier to move than protons, as we talked about this before, and the concept of being energetically favorable. But by then, this idea that current flows from positive to negative was already well established, and so it wasn't really easy to challenge that and then bring new change into science. And it's generally not that easy to bring such a large change. And so then they created this convention that electricity current flows opposite in the direction to which electrons flow. And so a convention is a rule that everyone has to follow. There doesn't have to be a logical explanation, but it's something that all scientists agree that they will follow. And so they all agreed that they're going to have this convention that electrons flow from negative to positive, and current always repels that. The current always does the opposite. So current always flows from positive to negative. And so then there became this convention that electron flow always opposes current flow, and vice versa. Current flow always opposes electron flow. Now that we're done with this, let's take a look at voltage. So to understand voltage, let's use an example first. Imagine I have a steel rod and I'm heating it from one side. So I'm transferring heat energy to one end of the steel rod. Now, I think we all know that if I was to give energy over here, the energy wouldn't directly reach the other end of the steel rod. This means that this area would have a high temperature and therefore a higher energy, more energy. So compared to this area, which will have less energy. Now, since there is a difference in temperature, what's eventually going to end up happening is that this high energy area or this high heated area is going to vibrate faster, right? And as a result, it's going to collide with all the other particles in between. And eventually, it's going to transfer the heat energy to the area with less energy. This is the concept of conduction, all right? And so now you may ask me, what does conduction have anything to do with voltage? Well, you see here, the thing that drives the movement of energy is the difference in energy. And so this is why voltage is also called potential difference. Because voltage is aimed at creating a potential difference. So basically, imagine you have a wire with a battery and a light bulb, let's say. And and how does the battery work? There's one positive side and then there's one negative side. Let's say you fill this negative side, and this negative side is filled with negative charge. So let's say this negative side, imagine, is just filled with electrons, and this positive side is filled with positive charge, or it's going to be relatively positive. If this is filled with electrons, it's going to be a negative charge, and so even if this is neutral, it's still going to be more positive. And so what ends up happening is that these large amounts of electrons move throughout the wire, and we already know this, is that this wire is a conductor, which means it already has it will already have electrons in it. And imagine this is a small wire. This is the positive side of the battery. This is the negative side. And what will happen is that this negative side will push more electrons, and so will give more electrons, and so it will push the already existing electrons forward, and so they will end up at the positive side. And so electrons will constantly be moving. And when the electron reaches the light bulb, it will transfer electrical energy. And so eventually what's going to happen is electrical energy will become heat energy. Oh, sorry, light and heat energy. Heat plus light energy. That's what's going to happen. And so this is how voltage works. So if I was to give you a definition, a proper definition, it would be something like this. The difference in charge between two specific points that causes current to flow. Okay? The difference in charge between two specific points that causes current to flow. And so let's break this down a little. Let me give you a bigger paragraph which makes more sense. For current to flow, from one spot it requires a potential difference. Otherwise, it requires a potential difference between 2 points. Between 2 points. Otherwise, the electrons will not be attracted and hence not move. And hence not move. Now, what is voltage? Voltage is the measure of this difference. And so, more voltage, and this is where it gets interesting. Remember this for later. This is an important note. Write this down. More voltage, because if there's a greater difference, let's go back to this pole. If I heat this even more, there will be more energy transferring to the area with less energy. And if I heat this less, there will be less energy transferring. So, in a similar way, if we create a larger difference in the charge, we can say something like, and so if there's more voltage, if there's larger difference, then there will be more current. That's something that we've seemed to establish, right? So we can say that voltage is proportional to current, right? That's something that we can say. And so this is where the concept of resistance kind of comes in. This is where we can find resistance. And so let's quickly take a look at resistance now. Let's take a look at resistance. But before we do that, let me just clear something about voltage. Voltage is measured in volts, that's the term, and the symbol for voltage is V. Unlike current, voltage is more simpler because for current the symbol is I and it's measured in amperes. Anyway, now let's look at resistance. Now coming back to my analogy of creating a potential difference with heat, we know that this place has high energy, right? And this place has low energy. And so energy is going to transfer. But let's say that whatever this rod is, let's say it's a plastic rod. Let's have two cases. First being it's a plastic rod, and second being it's a steel rod. Now I think we can all agree that, or copper, let's say copper. I think we can all agree that when it comes to transferring energy, the steel or copper rods will do a much better job than plastic. Why is this? Because plastic is an insulator, while steel and copper are conductors. Similarly, when it comes to resistance, something similar happens with electrons and how they move. So as electrons, this is something to note down, as electrons pass through a wire, their path is restricted. Their path is restricted by atoms that make up the wires. As electrons pass through a wire, their path is restricted by the atoms that make up the wires. So then you may ask, what are some specific factors that actually affect this? Well, let's take a look at the three main factors. The first main factor is the type of material. This is the example we looked at over here. Is your material that is conducting or moving electrons a conductor or an insulator? The second key thing that impacts is the length of the wire. If there is a longer wire, the energy has to travel a longer distance, and so transferring becomes harder. And the third thing is the thickness of the wire. If the wire is more thicker, let's say you have a thin wire and you have a thick wire. If the wire is thin, you have to cover a smaller surface area. But if you have a thicker wire, you have to cover a larger surface area, which means energy gets distributed more. Here, the energy gets distributed less. And so if you have a thicker wire, you're going to experience more resistance. And this is going to be less resistance because it's thinner and there's less surface area that the wire or that the energy has to cover. Okay, so now let's get down to the admin stuff. If voltage is measured in volts and the symbol is V, for resistance is measured in ohms. OHMS, ohms. And the symbol is omega. So resistance is measured in ohms and the symbol is omega. I hope this makes sense about resistance. And now, remember how we looked at how current is proportional to voltage? We're going to use that and then we're going to draw a relation between current, voltage and resistance. So let's quickly do that. And many of us know that that is Ohm's law. So let's take a look at this now. So now let's look at Ohm's law. In this part we'll look at all the theory, and in the next video we're going to do a bunch of difficult Ohm's law problems which will help ground and root our understanding of this concept. So first let's look at the first bit of information. So the current is found to be proportional to voltage. So I think we've already established this when we looked at voltage and resistance and current and all that. We said that if we were to increase the potential difference, the drive for the movement of charge would also increase. Like if we were to heat one side of that metal rod more, the movement of energy would be much faster. So similar to that, the current is found to be proportional to the voltage, right? And so this is written as V is proportional to I. Voltage is proportional to current. And so and in this case, we can apply a constant to relate these variables. We can apply a constant. And what is this constant? Well, with this constant, firstly, we can equate these variables. And what is this constant? This constant is resistance. So before we add this constant, we know that voltage is proportional to current. But after adding this constant, we know that voltage is equal to current times resistance. So this helps us equate, and this is just a proportional relationship. However, for this to be true, for voltage to equal current times resistance, all physical conditions remain the same. And this is where the concept of being ohmic or non-ohmic comes in. So imagine a component that is ohmic, right? This is going to follow this rule. Voltage is proportional. Voltage is equal to current times resistance. And so if we were to graph its current and if we were to graph its voltage, it would be somewhat like this. But if all physical conditions aren't the same, and so by physical conditions, we're mainly talking about temperature, humidity, all that kind of stuff. But mainly we're talking about temperature, because you notice that with light bulbs, they heat up. With halogen light bulbs, they heat up as you use them, and so they increase in temperature. And when something increases in temperature, its resistance also increases. So if we were to graph voltage and current, we'd get something like this. And so this is what we get for an ohmic conductor, and this is what we get for a non-ohmic conductor. You see here, if I was to calculate the gradient, and so now you may ask, why is current on the x-axis and why is voltage on the y-axis, even though in this case, the only thing you can change is the potential difference, right? The only thing I can change to create I can't speed up, let's go back to the steel rod. I can't speed up the rate of flow of energy, the rate of flow of heat energy, but by doing anything. All I can do is by increasing the temperature that at one end of the rod, and that will create a larger difference, which will mean that energy will travel faster, right? So why is it that if voltage or potential difference or the amount of heat energy that I apply is the independent variable, why is it on the y-axis and why is current on the x-axis, even though it is not the independent variable? Shouldn't it be the other way around? Well, let's take a look at this equation. Voltage is equal to current times resistance. Here, if we were to rearrange this, we would get resistance is equal to voltage over current, right? And so, in this case, if we were to calculate the gradient of this graph, we'd get voltage would have to be the rise and the current would have to be the run. And that is why voltage is on the rise side and current is on the run side. Because whatever this line is, that is our resistance. The gradient of this line is our resistance. And so, since the gradient is a straight line, we know that the resistance in an ohmic conductor remains the same. But a resistance for a non-ohmic conductor increases exponentially. So we can mark this as exponential increase. So from this, we established two things. That firstly, Ohm's law only works for ohmic conductors, and these are the conductors that ensure that the physical conditions remain the same. So a halogen light bulb would not be considered an ohmic conductor because, well, it heats up as you use it. On the other hand, a simple LED light would be considered an ohmic conductor because it doesn't heat up as much as you use it. And the second thing we established with this is we learned why voltage is on the y-axis and current is on the x-axis. It's because the way you derive resistance. So in reality, voltage should have been on the x-axis and current should have been on the y-axis. Y-axis, but in the way we look at resistance, it's the fact that it's voltage over current, and gradient is rise over run. So for this line to be the resistance, the voltage has to be the rise and current has to be the run. I hope that makes sense. If it doesn't, drop a comment down below and I'll explain it as best as I can. Okay, now let's look at some key points. This is an important table that we should all know, and it will help us with our understanding of Ohm's law. Okay, so let's look at case 1. Let's say the current remains the same. Okay, that means voltage drop will increase with the resistance. So if the current remains the same, if I increase the resistance, the voltage drop should also increase. So let's look at an example of this. So here I have 2 circuits. With the first one, I have 6 volts of energy. The resistance. Guys, so that kind of finishes off today's video. If you've enjoyed it, stay tuned for the next part. And this video I tried a little different. I added animations and all that kind of stuff. So I hope it helped in the explanation. Also, I added, the history behind it. So Benjamin Franklin and all that. I've tried to explain it as best as I can. But if there are any doubts, remember to just leave a comment down and I'll answer any doubts the best I can, the best of my ability. So the next video is going to be about solving Ohm's law questions, those difficult Ohm's law questions that we all scratch our heads over. And so, yeah, till then, stay tuned and I'll see you in the next video. The next video is also going to be, I'm also planning on giving an update on my independent research project that I'm doing over the holidays. And so right now I don't think it's going that well. I think we can maybe turn the tables with how it's going. But yeah, till then, stay tuned for the next video, and yeah, I'll leave it at here. Bye bye.